Hi, everyone. My name is Lauren Clayman, and I'm with the Radioisotope Power Systems program, which is at NASA's Glenn Research Center in Cleveland, Ohio. And you'll hear me say RPS a lot today, which is actually short for Radioisotope Power Systems. And for the program, I'm their Chief Safety and Mission Assurance Officer. I'm really excited to be here today to talk to you, and hopefully you'll learn more about our program and more about what I do, because this is a very exciting time for RPS. We have Perseverance carrying an RPS system, and I can't wait to share more with you about it. But before we get to Perseverance and Mars, I think it's important for you to understand more about what I do and the program and how we help power extreme exploration for NASA. So radioisotope power systems, or RPS, what do these systems do? Well, we actually provide power to go to some of the most extreme places in our solar system. I mean, at NASA, we are all about exploring, discovering, and then understanding what we get back from those discoveries. What's really cool is that in order to understand what's out there, we invest so much brain power into getting to these destinations in our solar system that we learn things that we can do better even here on Earth with the technologies that we use in space. And then we learn about the places in space and the planetary bodies out there and end up learning more about Earth's origin just from all these places we go and visit. And as you can imagine, compared to some of the environments on Earth, space is full of the most extreme environments that you can think of. They're really harsh, they're dark, they're cold, and they're dusty. And we send our missions there. And these missions would either be impossible or very hard to do without the use of nuclear power. And that's what a radioisotope power system is. An RPS harnesses the heat of the natural radioactive decay of a material called plutonium-238. And that heat from that decay is converted into electrical power, and we use that to operate our spacecraft systems and science instrumentation. And of course, I talked about how Perseverance has one of these RPS systems on it, but another recent example of when we've used an RPS system for a mission was the New Horizons historic journey to Pluto. That was made possible by an RPS system called an RTG, which is a radioisotope thermoelectric generator. And this is an RTG is exactly what we have on the Mars Curiosity rover, which is already up there on Mars, roving around. And like I said, what's going to be on the Perseverance and powering Perseverance. This particular type of RTG is called an MM-RTG. And the MM just simply stands for a system that was designed for more than one specific destination in mind. Therefore, it can serve multi-missions. So that's a multi-mission RTG. Now, I'd love to share a great video with you. This was made several years ago, back when Curiosity went up to Mars. The video explains how a radioisotope power system works, but specifically an MMRTG. So just keep in mind, this was on Curiosity, and this is what's on Perseverance, which is going to land later today.
If you want to drive a rover on Mars, you have to keep in mind, there's no gas station for millions of miles, and there's no outlet to plug into for power. That's why NASA's Curiosity rover on Mars and other NASA spacecraft that explore the solar system use something called radioisotope power. A radioactive substance releases heat as it breaks down or decays. A system that converts that heat into electricity is called a radioisotope power system. These systems get fancy names. Curiosity's power system is called the MMRTG. Multi-mission radioisotope thermoelectric generator. MMRTGs are reliable and last a long time. Engineers use this material in devices called thermocouples, which are used to generate electricity. One of the thermocouple shoes is hot and one is cold. This heat, transferred across a big temperature difference, makes electrical charges flow from the hot shoe to the cold shoe and produces an electrical voltage. And this generates useful electrical power.
All right, great. I love that video because I think it breaks down exactly, what's happening when the heat is released from this radioactive material, and the fact that we just take that heat and turn it into electrical power with these things called thermocouples. And now it gets to power things that we send up into space. And I want to show you this picture. It's a picture of Perseverance. And I don't know if you can see very well there. It's on the back of this rover, and it's painted white. There's a dotted line showing you exactly where this MMRTG is. So you can imagine this particular rover is, I'd say, roughly the size of a large golf cart or a small vehicle. And this MMRTG is giving off the amount of power that I think all of us are kind of used to thinking about. This is just a standard 100-watt light bulb. I have these in my house at home, and this MMRTG is creating just over that, 110 watts. And all that power is all that's needed to help this rover move across Mars and do its job. So I think that's a big testament to the ingenuity and brilliance of these great scientists and engineers we have working in the NASA community, to be able to build this kind of a spacecraft with power that's equivalent to about a light bulb, and it can run on that. So I always, that kind of blows my mind a little bit. I always like to let people know, because it's kind of a very crazy thing to put in parallel with just a light bulb. Now I have another video for you. This is a much better close-up of an MMRTG. And I'll play this video and kind of try to describe a little bit about what you're seeing here. So the cylindrical portion in the center is actually where the nuclear material goes. And it's surrounded by all these little thermocouples that are taking the heat and turning it into electricity. And if you want to break down a little bit more, these heat sources made of the nuclear material, they're in these things that look like bricks called GPHS, or general purpose heat sources. And the main thing to note here is that you see these sort of orangey peach colored pellets. That's the nuclear material. And there's lots of protective cladding over it. And there's basically layers and layers. So once you can see how all the layers fit together to go inside of this GPHS, they're all stacked up and put in the center of this MMRTG. That's where we keep all of the heat that's turned into electrical power. So I really like this animation because it actually gets to show you how everything fits together. And I know that helps my mind understand things quite a bit. And then all this energy is transported to the spacecraft for use. And you might wonder what those little spokes are coming off of this thing. And those are just spokes for releasing or radiating off some of the extra heat that comes from this nuclear material. We don't take all of it, and we can't convert it all to electricity because we don't have a process that's efficient enough to do that. So we have waste heat, and we either radiate it, or sometimes spacecraft even use this waste heat to keep their other instrumentation warm enough. Because in space, in the harsh environments of space, you can't let certain things get too cold. So we can provide power, and in some cases, we can provide heat to spacecraft as well. But when we think about RPS systems, I know our program likes to refer to something we call the 4 Ps: people, power, progress, and production. Because by nature, we are explorers, and it all starts with people. The RPS program is actually part of NASA's Science Mission Directorate's Planetary Science Division. And I mentioned before, we have some really passionate, bright people working for this group. And part of the responsibility I have as the Chief Safety Mission Assurance Officer for this program is to enforce NASA's top priorities, which is safety and, of course, the success of our missions. The safety of the public and of our NASA teams is always, always our top priority in our quest to succeed with our missions. So obviously, I take that very seriously, and I get to work with a lot of experts who know how to ensure that everything that we do during the design, testing, and launching of an RPS all happens safely. So I'm kind of here as a resource or a checks and balance type of function to help make sure everything works well and is successful. And of course, the second P, power, we talked about that already. We provide power for spacecraft, for robotics, so that we can explore these amazing places our solar system has to offer. And I think it's just quite amazing when we think about the amount of power that we're able to get by on using to make all of these amazing things happen. And of course, even though we have these systems today, we're always pushing the boundaries and trying to improve them. Our program is continuing to invest in new technology and improvements to those technologies so that we can make better systems and make them more efficient. And then in the end, NASA and the community at large, we're going to lead to even greater science returns. And then production. Why is production important? Well, we talked about nuclear material being the fuel for these systems. And we've gone roving on Mars using these systems, and we're looking for, in the future, a mission called Dragonfly that plans to go to Saturn's moon Titan. We're going to have an RPS system there. And by adding missions back to the moon and and even more, missions to Mars in our future, the RPS program has taken steps in partnership with the Department of Energy to make sure that we have enough fuel or radioactive material that makes the fuel for our RPS available. And we're doing this with the DOE through something they've established called constant rate production. That just essentially means that material is continuously being produced, and so that once we can gauge what the future needs of NASA are based upon future missions that are planned, and then we'll have this fuel and material available when these missions are finally ready to launch. And this is also pretty significant because in doing this, the Department of Energy has reestablished the United States production of this material. And this was just within the last several years. About 30 years ago, we lost the ability to do that, in the United States. So that's pretty cool for us. And a fun fact is that some of the first produced plutonium-238 is even in the heat sources that are going to be powering Perseverance. So how cool is that? All right. Well, I mentioned that we have a great history of utilizing RPS systems for some of NASA's missions. Here you can see, this is kind of an eye chart, but there's 25 missions from the Sun to Pluto and beyond. A number of those are Mars missions right over here. We're building a pretty successful resume of missions that we've supported with RPS system. And that helps build our confidence that these systems are reliable, that they're safe, that they're long lasting. So for me in my position, gathering this type of information and data on the performance of all these systems help to demonstrate, that, they're long lasting and safe. And that's what's important for us to do always at NASA. And we often get asked why we use plutonium-238 and not something else. And really, the truth is that there are other materials, nuclear materials out there that are radioisotope materials that would work. But this particular material was carefully chosen for a number of reasons because those things made it technically and safely compatible for our RPS systems. And as I mentioned before, one of the MMRTGs that's on Perseverance, one of them is on Curiosity, which is there right now. And what I like about showing some of these pictures that Curiosity had sent back is that they're strikingly Earth-like, even though they're extraterrestrial. I mean, I love the bottom middle picture. It really does kind of just look like someplace, I don't know, maybe in New Mexico or something. But, this did a lot of excellent work, taking samples of rocks and soil and taking pictures back for us. And what's really cool about this rover is that it's, it's been like over 3,000 Martian days, we call them souls, since Curiosity touched down in August, I think, of 2012. So it's actually worked well beyond its intended life and keeps making new discoveries. So let's all keep our fingers crossed that that's going to happen just the same with Perseverance as well. Speaking of Perseverance, this rover here, and it's one of the top left pictures. This is a picture of it launching. It actually launched on its journey to Mars back in July of 2020. And below it, you can see actually a picture of when it was getting assembled in a clean room with the rest of the rover. The MMRTG is getting, installed onto it. And I think I'll talk more about this picture in a few minutes. But the two middle pictures are pretty cool because since Perseverance is actually the first part of a 3-part sample return mission, we're going to end up learning about soil and rock samples that the rover collects on Mars, but we're also going to be testing the technology to launch a spacecraft off of the Mars surface, which has never been done before, and then rendezvous and dock around Mars for a return trip to Earth, which has also never been done before. So, this is a really, really interesting thing, and it's going to be the proving ground, I think, for a lot of our future Mars exploration. And, really robotics, they do pave the way for human exploration. They provide us with a better understanding of the conditions of the destinations that we go to, like the geology or the atmosphere. We learn if there's water present or if it looks like there's signs of water having existed previously. And really all of these types of robotic missions become a precursor for human exploration. Not only how we can make these areas habitable, but also testing new technologies first before we do that with humans so that we don't put lives at risk. And what's really cool too is the Apollo missions that went to the moon. They also had robotic precursor missions. I think it was called Ranger and Surveyor. And those missions were used to determine how best to land humans on the moon and return them safely home. So as I mentioned, it's so important for the science to be done. This Perseverance is going to collect, you can see in the bottom right, is a depiction of a sample of rocks it might collect. It's going to, take about 20 samples and leave them on Mars, and they will be intended to be picked up by a future mission and brought back home so that we can actually study Martian samples on Earth. All right. Well, so in our journey to Mars, of course, we have to integrate our MMRTG, which you see here, in with the rest of the flight hardware. It's really important that the system is safe while it's here on Earth, but also when it reaches its destination. So, my job has a lot to do with ensuring safety. And one of the ways we try to keep things safe for use on other planets is through the extreme cleanliness measures being taken here on Earth. So we use rooms called clean rooms to assemble our hardware. And as you can imagine, the cleanliness of these rooms is very, very tightly controlled. Technicians have to wear protective clothing at all times, really from like head to toe. And, so keeping these rooms clean for the hardware and all the people in the rooms free from transferring contaminants to the hardware, we're not only ensuring that we don't scratch or gunk up the hardware, but we're keeping biological contaminants off of the hardware, so that whatever we send to another planetary body is free from anything that we might have brought from Earth. We don't want to take any of our biology there. Whatever we find on Mars, we want to know it's really from Mars and not something we brought from Earth. And here's really another picture kind of from a different angle and with people in it. So it's kind of what you just saw. But I love this picture because it gives you the sense of scale for how big this is. It really is kind of like the size of a small golf cart. And here you can see the technicians helping to install this. This was actually what's called a hot fit check, wherein the MMRTG is being loaded onto the rover. And the hot part of hot fit check simply means they're loading in the fuel, because once the fuel is in there, you can't stop radioactive decay. It stays warm. This thing is going to be generating heat. And so this is what's called a hot fit check. They have to make sure everything is integrated properly. But these are real people who are able to be around this radioactive material because of all the safety being built into making the heat sources, from how the material is produced all the way to how we have fully safeguarded the system that's integrated with the rest of the rover. And now since you have been able to learn about the MMRTG that will be on Perseverance, this is a cool animation, and you might have seen something like this before, or you will see something like this later today, but this is basically the landing sequence that will be happening in just a few hours. And now hopefully you can pick out and see where the MMRTG is in this short video clip. You see it? There it is. I love that video. It's hard to believe that that's what's going to be happening later today. But another fun fact is that I think the Mars distance from Earth today is about 127 million miles, and we get to see this landing near real time as it's happening on something that far away. And I also find it very cool to know that this thing is going to be plummeting through Mars atmosphere at like 12,000 miles per hour, something like that. And it's going to get slowed down to roughly something about 2 miles per hour before it lands on the surface of Mars. So I don't know how these engineers do it, but it's going to land slowly and softly, and landing on Mars is quite challenging. All right. Well, one thing I like to share with everybody is that we have the RPS program has a really great website. It's at rps.nasa.gov. And one of a really cool new feature that we have on the website is this thing called Power to Explore experience. It's a 3D viewer wherein you can go and take a closer look at the MMRTG on NASA's Perseverance rover. So I really encourage you to go and try to interact with this new 3D viewer on our website. And like I said, here's the website again. We have I think all the videos that I showed today, as well as quite a few more on there. We have excellent resources. You can learn more about other RPS systems, all of the missions that we have had RPS on. And I really hope you go take a look at this website. I'm so happy again for having been here with you today. I know that Perseverance is, I think, the most sophisticated rover that we've ever sent to Mars. I mean, it could be one of the most sophisticated and complex spacecraft that's ever gone into space. And I know the name Perseverance really embodies all of NASA's passion for taking on and overcoming challenges. So, you know, in the future, when we go from Earth back to the moon, you know, more missions to Mars, the power for robotic and human missions is going to be really critical, and these nuclear power systems can really pave the way. So thank you so much for your time today. I really enjoyed talking to you, and enjoy the landing later. Thank you so much.